In order to decide whether or not the descriptions we create from our descriptive statistics are reflective of what is going on in the larger population, we need to know what could happen. You gather information. Did you do it well? Did you get a good sample? Do we have a good response rate on our instruments? All of those questions we asked about bias and selection. Did we get it right? And if the answer is yes, then I can start looking at my data under the assumption it is correct and ask, how likely is it that this reflects an accurate picture of what's really going on out there? To describe should is a problem. So I think of what's going on as an experiment. And it's literally any process whose results are not predetermined. If I throw a ball into the air, it will eventually hit the ground. That's deterministic, 100%. Until we live in the Avatar universe and unobtainium is a thing, I'm not worried about that not happening. If it's not predetermined, there are possibilities. I flip a coin into the air, then there are options, right? We're going to call those outcomes. I brought one with me. If there's a collection of outcomes, I should be able to list them all. That list is called the sample space. It doesn't have to be in any particular order. It's just a set of options. The items in S could be any type of data. I could have nominal, categorical data. What are the outcomes for my coin? I hope so. Heads or tails. That's it. If I really want to be technical about it, there's a third option. But if I'm just flipping the coin and it's not going to land like that, right? There's a bet in Vegas. You pay $1, they give you $1 coin. They strap your wrist to a table. They put a bar 12 inches above the surface of the table. If you flip the coin over the bar and it lands on edge, you win $1 million. Hasn't happened yet. So we'll ignore the things that are damn near impossible. But we should figure out what that means. I have a list of 2 outcomes. Those are nominal, right? Heads, tails. They're just names. I'm not labeling them. They're not quantities in any way. I can look at numerical data. What's my list of outcomes? The numbers one, and those are discrete, right? On the other hand, if I asked you to measure how far this die rolled when I threw it, that could be continuous, right? It could go from 0 to however, and we could measure it to any accuracy. So I can have discrete data, I can have continuous data, I can have quantitative data, I can have qualitative data. All sorts of things can be in my set of outcomes. I could create subsets. When I have a set, I can just pull a bunch of them, call it another pile. There's my sample space. Here's a collection of things from them. I'm going to name my sample space. I'm usually going to call it S. And event E is then a subset. A simple event is one outcome. It's also sometimes called an elementary event. So if I have, as Felix said, the outcomes for a fair die, one die with 6 sides, 1d6, my sample space consists of these 6 numbers. Assuming this die is fair, it's not loaded or biased in any way, then all of these events are equally likely to occur. If I roll this die, there's just as much chance of it coming up 1 as 5, as 3, as 6. Again, I flip a coin. The outcomes are heads and tails. Assuming the coin is fair, there's just as much chance of heads as tails. Again, that's an assumption, assuming the coin is fair. I haven't weighted it or balanced it awkwardly, or I don't have a technique for flipping it.
I was gonna say, a regular coin is more likely to land on tails than it is heads because of the carving on the front.
Because the head actually has more mass than the tail in certain coins. This happens to be one of those Sacagawea dollar coins. And if you look at the carving on the front versus the carving on the back, there's actually not quite as big of a difference between the carved area on the back versus the carved area of the front. But again, that would make the weight different, right? So that's the issue. I believe the least fair coin in that fashion is a dime, because the difference between the front carving and the back carving is so substantial. Most of the front of the dime is Eisenhower's head, and the back is only the 3 torches. Well, the torch and the fascia. And this is only American coins. I don't know what the euro setup looks like at all. I happen to at home have a loonie or a toonie, but that's a separate issue. Felix, talk to me. What's unreadable?
And what's the sign in the middle?
That's a D. 1d6. One die with 6 sides. Because I have lots of dice. And some of them are different. How many sides do you want? 4, 8, 12, 10, 20. 160. How many sides do you want? What's interesting, these dice are fairly old. Therefore, they're probably not fair anymore. Some of them are chipped, and this is about a year old. This is, as far as I can tell, a fair die with 160 signs. It's ridiculous. I bought it because it was ridiculous. But the role-playing games all use 20-sided dice. The logo is a 20-sided die for a lot of these games. That's this logo. It happens to also be the logo of the Math Association of America. Most of those are called D20 games for that reason. It is possible to come up with a set of outcomes that are not equally likely. We've just listed ones that are equally likely. If I roll 2 dice, what would the list of outcomes look like? Depends on what I do with them, right? Most dice games that have you roll 2 dice have you add the numbers. So if I roll the dice and add the numbers, what's my sample space look like? All the numbers from 2 to 12. But there's only one way to roll a 12. How many ways are there to roll a 7? Lots. I could roll this, right? I could also roll that, and those are different. I could roll this, or I could roll this, or that. Oh, wrong way. That, or that. I have 6 different ways to roll a 7. That means the chance of getting a 7 and the chance of getting a 12 are different. Those outcomes are not equally likely, even if the dice are fair. In the textbook, there's an example about just trying to list sample spaces. On page 155, there's an example about going to a bookstore, and what do you buy at the bookstore? Well, if you go to the campus bookstore, what do you buy at the bookstore? There's books, there's clothes, there's supplies, there's lots of stuff, right? So I can say, these are the things that people buy, make some categories. Buy a book, you buy clothing, you can buy sundries with the other stuff. How do you pay? How do you pay for the thing you buy at the bookstore? How are you physically giving the money to them? Did you pay in cash? Did you pay with a credit card? Did you pay with a debit card? Did you, archaically old people, did you pay with a check? Right? So there are different ways I can, but what's my sample space look like? Well, I have 3 options of things people can buy, and I have 3 options of the way they pay: cash, credit card, debit card. And I want to keep those as separate because I get charged different fees for credit versus debit. And I have to charge different taxes on books versus clothing versus sundries, because the state of Pennsylvania is weird about what gets taxed and what isn't. So now I'd have to make the list of what my options are. But my options, I'm looking at the elementary events. I bought a book. I paid cash. That's one outcome. I bought a book. I paid with a credit card. That's an outcome. I bought a book. I paid with a debit card. That's an outcome. So my list is not single items, but object payment as an item. If I asked you to pick a student at random in Seton Hill, there are 2 pieces of information I want to know. What school is their major in? Natural and health sciences, visual and performing arts, humanities, education and applied sciences, or business? What year are they? Freshman, sophomore, junior, senior. Now, if I'm truly picking from the student body at random, I should have a category: graduate. I got 5 schools and 5 options, right? Okay, pick a student at random. How many possible results are there? Natural and health sciences, visual and performing arts, humanities, education, business. Freshman, sophomore, junior. I already used S, so I'll use R, senior, and graduate. The outcome for a student could look like that. All 5 of those students happen to be in the School of Natural and Health Sciences. I can keep going, right? Replace all of those N's with a V. And so on. Are these equally likely? Why not?
Don't have the numbers. There's a whole bunch of people in business right now, and they just all joined, and there's way more of a likelihood of you getting a freshman in business course.
Freshman in the business school, right, yeah. And we know that there are only a couple of graduate programs at Seton Hill, and most of them are in business or humanities or sciences. As far as I know, there isn't a master's program in visual and performing arts. I don't think there's a master's in music, a master's in theater, or a master's in teaching. There is a master's in education, but there are only 2 programs that are masters in education. There are 5 MBA programs. There's the writing popular fiction, which is technically a graduate program, but only kind of. Ooh, there's all sorts of weirdness going on here. So they're not equally likely. I have a list of outcomes. There would be how many more?
Yes, 5 possibilities.
Okay. So how many more do I need to write down to list all of them? It's now 10. 15 more to get a total of 25 different outcomes. Absolutely. Now, once I have the list, once I have my sample space, my events, my simple or compound, my goal is to try and figure out within a sample space, how likely is something? What's the chance you pick a student and they're a freshman in business? I have no idea. I have no idea. But that is the definition of probability. The probability of an event. Let's call the event A within my sample space S. Then we would write P of A to mean the probability of event A. This is a relative probability. Sorry, a relative likelihood. So I'm going to be comparing things. P of A is a number. There are some things I can guarantee you about this number, even before having done anything. This number, P of A, what's the smallest it could be? Smallest possible value for a chance. I got no chance at all, right? You roll these dice and add the numbers. The chance your total is 13. Not gonna happen. Interesting story. In Norse mythology, Odin, no, it's in Norse or Greek. I don't remember anymore. The three brothers are playing for who gets which kingdom. Who will be kingdom of above, of below, and of the waters. I think that's why I'm remembering it as Norse, because it's Odin and Poseidon and Hades. I think. And they roll dice for it. And Poseidon rolls a 12. Beat that. And Odin picks up the dice and hurls them against the wall. And rolls a 6, and the other one breaks in half and shows a 6 and a 1. I got a 13, I win. I don't know if it's a great story. But this number must be bigger than or equal to 0. What's the biggest that number can be? Something that's going to happen. 100 and 100% means 100 out of 100, which is 1. So every time I do a probability, I should get a number between 0 and 1. And if I get 0, that's never going to happen. And I get 1, it's always going to happen. An event can be impossible or it can be guaranteed, certain. If S is a set of events and all of these events are simple. I'm sorry. Those should be my outcomes, not my events. So each of those is just one thing. Like we're rolling the die. 1, 2, 3, 4, 5, 6. Then the sum of all of the chances must be, you've listed out all the possible things. Must be 1 again. One of them is going to happen, right? So the total of all the chances of everything happening has to add up to 1. Questions so far? I ate my other coin. I'll find it. how do I figure out in any sample space, how do I figure out the probability of an event? There are three typical methods for determining probability. The one I like the least is called judgment. You've done this a bunch, you've seen some other things. It's a subjective opinion. So, one, subjective. You go with your gut feeling. You have an informed opinion. You think you know what should or shouldn't happen. Not to be judgmental or anything, I hate this. Two, you can do an experiment. Empirical means I did an experiment, I got a result. But I don't do just the experiment once, I do it a bunch. Wait a minute. I gather a bunch of data, and then I look at relative frequencies. This is basically building a histogram. Now that is useful. I do the thing a bunch and I see what happens. And I just count. And the third option is theoretical. I'm going to use some sort of knowledge of the process of the experiment itself to determine the chances before I even do the experiment. Page 156. This is a lovely little table about views of probability, and these are our three views. I did them in a slightly different order, but here they are, page 156. You are having a child. Congratulations. What is the chance the child is male or female? I have no idea, right? But let's think about that through each of these lenses. If I were doing subjective probability, I might look at your family history, your mother, your grandmothers, your great-grandmothers. Do boys or girls run in your family? I can use that and then make a judgment, right? There's no math there. There's no experiment there. There's just an interpretation. I'm trusting my gut here. You hang the ring over the mother's belly, and if it turns clockwise, it's a boy, and counterclockwise, it's a girl. I don't remember what these old wives' tales are, but empirical. I go down to the hospital, and I go to the maternity ward, and I say, of the babies born on this day for the past 10 years, how many have been boys and how many have been girls? Well, that's the day your baby is going to be born. I'd like to know about, or maybe I go for the past 3 years. How many boys have been born at this hospital? How many girls have been born at this hospital? Maybe I look at the whole county. Maybe I look at the whole state. I can actually just do the experiment. I'm not going to make you have all the kids, but I can gather that information. Theoretical. Well, all right. Gender is determined by the father's genetic component. Sperm counts and sperm motility and genetic, and then I can do an analysis of his sperm. And I can make do a theory about this. And it turns out we can get some numbers that way. I'm not sure I know enough biology or anatomy to do that properly, but we can go get someone from the biology department. Empirical seems to be like it would be most useful in this case, right? I can gather information about what's been happening in this area. I can do some guessing based on that. But if I'm doing the experiment over and over, let's go with an easy experiment. I'm going to roll that die. If I roll that die 10 times right now, what's the chance I roll a heads? Heads. What's the chance I roll a 6? I did it. Chance I roll a 6. I flip a coin right now. What's the chance that comes up heads? Empirical probability means I should do it a bunch and see how many times I got a 6. So far, I've only gotten one. Up there's 2, 3. Oh, that was a 5. All right. Out of 10 rolls, I got 2 6s. So I would say the chance of getting a 6 is 2 out of 10. The probability of A is the number of times A happens divided by the number of times we do the experiment. I only rolled this die 10 times. If I rolled it 100 times, I would get a different number. If I rolled it tomorrow 10 times, I might get a different number. If I roll it 10 more times right now, it might not be 2 out of 10 again. But all I'm doing is I'm counting how many times did the thing we want to have happen. Batting averages. How many times you get a hit versus how many times you went to bat, right? That's it. That's all that is. It's a probability. There was a news article yesterday on the radio about Major League Baseball and the fact that this is one of the lowest hitting seasons in the majors ever. The number of people hitting 30% or better is the lowest it's been since the 1980s. 80s? Carl Yastrzemski won the batting average with a 301 that year. That's the lowest batting average to ever win the competition. So, this die has a 2 out of 10 chance of rolling a 6. Does that make sense? Ten shots isn't a very good number of tries, right? That's a low number of experiments. So maybe I need to jap this number up quite a bit. But if we think about this in our frequency distribution, this is the frequency of our event over the number of times we did it. That's exactly the column for percentage relative frequency. It's exactly the way we got that calculation. If I jack that number n up, I'll get a more accurate thing. I flip a coin. Heads. So the chance that coin comes up heads is 100%. I just did it. Wait a minute. Doesn't make any sense. I have to do the experiment a reasonable number of times. I have to gather the data a sufficient number of times to say this is accurately reflecting what I think should happen. It turns out there's a very nice rule. Called the law of large numbers. The law of large numbers says that as n gets bigger and bigger and bigger, the empirical probability gets closer and closer and closer to the theoretical probability. The problem with this sentence is that I haven't defined how to get theoretical probability yet. Empirical probability is easy to get. Just do the experiment a bunch. But theoretical probability is not as easy to actually get. Unless our situation is fairly simple. Felix?
Yeah, that is very simple.
Right? Because there's a very small number of possible outcomes. Let's go even easier than that. Let's go back to our coin flip, right? If you were doing a theory idea, you flip a coin, what's the chance it lands heads? 1 means something certain to happen. As a probability, 1 means it's 100%, it's going to come up heads. I flip a coin right now, it's guaranteed to come, 50%. So if I flip a coin once, clearly I can't get half of it to be heads. But if I flip a coin twice, I should get 1 head and 1 tail? Not necessarily, right? Here's what the law of large numbers tells me. If you start flipping coins and keep track of the relative frequency of heads,
You just multiply the probability that it comes once and then we go on. Like,
I'm just actually talking about getting the data. Here's my coin. Flip the coin. You got yourself a table. What did you get? Heads, tails?
yes.
You got heads. Flip it again.
Hey,
Okay, that's 1 and 1. Flip it again. So now I have a 50% of heads. Flip it again.
oh, it's again, so it's
So it's now 1 out of 3, right? But that's below 50%. I went from 1 head, 50%, 33%. And if I keep going, what's going to happen in the long run? According to the law of large numbers, my fraction should get closer and closer to a half the longer I go on. So on page 158, I see the results of flipping a coin first 10 times. The first 3 flips were all heads. I got heads 100% of the time through number 3. And then the fourth one was a tail, so it's 75%. The fifth one was a tail, so it's 60%. Oh, then I got a head, then I got a tail, a head, a tail. By the time I got to here, I'd have 5 heads and 5 tails. But I kept going, and then I got a couple more heads and a couple more tails and a couple more. See how it's starting to weave? But as I go from 20 to 50, hey, look at that. What happened there? A run of heads in a row, right? And then here's 200 flip. In the long run, we get closer and closer to 50%. But I'm not required to be at 50%. As a matter of fact, you will almost never be at 50% until you've flipped millions of coins. So one of the questions we have about doing the experiment is, have I done enough experiments? We only did 3, and you said heads came up 1 out of 3 times. Okay, chance of this coin landing on heads is 1 out of 3. Maybe it's not as cheap as flipping a coin. Maybe this is an expensive procedure. Maybe I'm trying to figure out something that might actually be life or death. I don't want to do that experiment very often, right? Is the process done exactly the same time every time? It's kind of hard to flip the coin exactly the same spin, exactly the same height. Ooh, can I make that happen? Can I fix the variables so there's less variation? Is the process stable over time? If you were asked to use a saw to cut a piece of wood, and we measured the piece of wood you cut, you were asked to cut a piece of wood 1 foot long, and we measured it over and over and over and over and over. Over time, what happens to your saw blade? Say that again.
Gets dull.
Gets dull. As the saw blade gets dull, the cuts get wider. So all of a sudden, my length of board goes down a little bit. Is the process stable over time? Flipping coins, I'm pretty sure I can do that the same, or at least very similar, over and over. But it might be that there are outside factors that prevent or override my ability to gather this data. There was a very big push on this 5 years ago. If I want, it's going on right now, today in Washington, D.C. They are discussing the trials for vaccine, like the COVID vaccine. 5 years ago, there was a big push to say, we are only going to do this kind of trial instead of this kind of trial. We're only going to do data this much instead of doing all the data this much because people are dying. And so the vaccine came out with a smaller set of trials than would otherwise have come out. Are repeated trials even possible? If I'm checking car bumpers for impact resistance, you're going to slam into the same bumper 10 times? It's not going to be the same after the first hit, is it? So it may be that we can't do this empirically. And if I can't do it empirically, I want to do it theoretically, because then I at least know where I'm going with my repeated experiments. And I can tell if something unusual happens. So I want to work on defining theoretical probability. Theoretical probability rides on a couple of assumptions. It rides on the fact that I can list elementary outcomes. I can get a complete list of elementary outcomes. So with our dice, this is 1, 2, 3, 4, 5, 6. If I'm only rolling 1 die. Even if I'm rolling this monster sucker, that's the numbers from 1 to 180, 120, whatever it is. I can make the list. I took out the jokers. Pick a card. You can make a list of all the outcomes, right? How many outcomes are there? How many cards in a deck? Okay, your homework for this weekend is to go buy a deck of cards. Say again? There are 52 options. There are 13 in each suit, 1 through 10, Jack, Queen, and King, available in hearts, clubs, diamonds, or spades. 13 face values, 13 values, and 4 suits in a standard deck of cards. There are other decks. But I have this list of elementary outcomes. The other assumption is that every outcome is equally likely. So I'm not looking at forced cards. I'm not looking at anything particular. I'm not saying, hey, this deck happens to have 3 ace of spades in it. It doesn't. So the chance of getting a queen of hearts is the same as the chance of getting the 3 of clubs. Let's pick an event. My event is going to be that I draw an ace. I don't care what suit it is. I care that the value is an ace. So there's my event. It's made up of 4 outcomes. Out of, what was that number, Helen? All I have to do is take the ratio, which is the same ratio as our empirical probability. The chance of the thing I want to happen. How many ways can what I want happen? Out of how many ways can something happen? In my standard deck of cards, the chance of pulling an ace at random is 4 out of 52. Because there are 4 available aces, the number of things in my outcome, out of 52 possible choices, the number of things in my sample space. Which means when we start doing theoretical probability, what we really have to be doing is counting things. These calculations are done in advance. I can tell you that this number is 4 out of 52 before you even touch the deck of cards. Before we shuffle, before we do anything else. I am not a card magician at all. So I guarantee you I'm not going to rig this deck. We could do this shuffle by playing 52 pickup and throw the deck into the air. It's still 4 out of 52. These are based on pure logic, on our ability to count. This isn't always practically available to us in business situations. If we're lucky, it is. Subjective is I asked an expert, in which case we hope somebody knows what they're talking about. Okay, Felix, you said something about multiplying.
Yeah, just that we asked about it, how high is the probability that we get it 10 times the 6?
Well, but it's 10 times, yeah, if I roll a 6 out of 10 times, how many should I get? That's a rule I'd like to understand a little more. There's got to be something in the discussion about how I do that, and that's what we'll pick up on Monday. And on Monday, chapter 4 is due, and on Wednesday is the exam. If you look carefully, you will see something really nice about next Friday. We don't have class because I have to go to a career fair. That's where I will be. So we will not have class on Friday. So we'll do this on Monday, talk about the rules some more, and then we'll take the exam, and then I'll give you a day off. Enjoy the rest of your day today and your